Good afternoon to all from the editorial board of BuildUp portal. For the ones who are attending a BuildUp webinar for the first time, welcome. For our returning audience, thank you for renovating your interest. Just a brief explanation of what is BuildUp. BuildUp is a collaborative platform in the field of energy efficiency in buildings. It is continuously updated and it represents one of the key sources of information on the topic of energy efficiency. You can register and become a member of the community, and you can also upload news, events, present case studies, results from projects, and so on. I would like to invite you all to navigate the portal. In the Learn section, you will find all the podcasts of the past webinars, so it is possible to listen to all the previous presentations. At the end of this webinar, the link to the full presentation and the file to the PDF presentation will be made available in this section of the portal. It is a pleasure to host today's 7th webinar of the EPB Standard series entitled Example Calculations with a Set of EPB Standards, Introduction and Overarching Calculation Procedures, which is organized in collaboration with the EPB Center and REVA, the Federation of European Heating, Ventilation and Air Conditioning Associations. As you can see from the screen, we have scheduled a series of webinars on the topic of the EPB standards. Take a note about the next webinar, which is taking place on the 20th of October at 12 and is entitled Example Calculation with a Set of EPB Standards, Energy Needs Combined with Specific Systems. I would like to invite you all to contribute and participate in this webinar. You can ask questions by typing in the box on the right side of the screen. The questions will be answered at the end after the presentations. And now I would like to present the agenda of today's webinar and introduce the 3 panelists. First, Jaap Hogeling, who is part of the Energy Performance of Buildings Project Group and the European Committee for Standardization, will introduce the examples calculation, why and how. Then, Dick van Dijk, EPB expert from the EPB Center, will explain the first series of example calculations on energy needs. And finally, Laurens Sokal will discuss about the overall energy performance indicator. So now I would like to leave the floor to Jaap Hogeling, and please we can start the session.
Good day to all of you. Thank you for your kind introduction. It's a pleasure for me to give this introduction to this series of four webinars on example calculations in the framework of energy performance of buildings, supporting the implementation of the Energy Performance of Buildings Directive in Europe. The background is already said. I'm chair of 371, which is the CEN committee in CEN to develop the EPB standards project. And I'm also participating in the 5 technical committees in Europe where all the standards have been developed, and the 2 ISO TCs that also cover this area. My background is manager international standards at ISO the Netherlands and initiator of the EPB Center, an initiative from ISO and REVA. I very often present this picture. You may know because I presented it in several times. It gives you just an idea about the set of almost 50 standards and their interconnection. You see on the top the input values you need for the heat gains, the building properties, the climate conditions, and the environmental conditions, and also the user patterns, which are the basis for the energy need calculation, as will be described also by Dick van Dijk on the Vision 2016. And then this is the output of this calculation is of course the input for the system calculations on cooling, ventilation, heating, domestic hot water and lighting, taking into account the effect of building automation systems and controls. And finally, it lands on the overarching standards where you have the final expression on the conversion to primary energy and other expressions you want to follow. This will be presented by Laurent Socot. It's clear that this total set has to work together, and the goal of this project to make example calculation is to demonstrate the functionality. And the calculation works together on practical cases, how available features are possible to show, and how different installations for heating, cooling, and ventilation are working in the set of EPB standards. Are the standards sensitive in the impact of the data variation, and are they usable? Clear data input description of practical system configurations, and useful results to avoid unnecessary input complexity. That is what we try to demonstrate for individual modules, but also for a whole building calculation. Why? It is a request also from many member states to us show how it works. It is the most convincing way to demonstrate that the set of EPB standards is functioning. Based on the current set of spreadsheets, demonstrate the functionality and the sensitivity of the individual calculation modules and their combination. That is why we want to do it. How? Of course, first we have to describe the buildings, its technical systems. For this demonstration purpose, it is not necessary to use a very complicated building. However, it is still an extensive task, I must admit, because this will require a long list of elements, properties, and several alternative systems to describe. First, we will demonstrate that the individual modules work properly. And of course, there are a lot of variations. We have to consider climate, user profiles. For the climates, we choose for the cold climate Oslo, the mild climate Strasbourg, and the warm climate Athens. This choice represents more or less the variety in the climate in Europe, and this selection is also used where relevant as basis for the European product database for energy labeling of energy using products. So that is also good to harmonize this at this moment. We have, of course, to define user profiles. This will be based on the profiles that are included in the standard 16798-1 on the indoor environmental input parameters for energy calculations. And then we have to show the coordination between the modules. Several modules will be tested together to see the effect of the interrelation between the modules, typically to see the effect of operating conditions. The collection of modules will be tested by connecting spreadsheets, and software will be used to generate relevant input, because connecting spreadsheets is not that easy and obvious, so we need some software to help us to do that. For this task, this means we have to identify appropriate calculation cases and related input data sets. Buildings, well, we think of the following, at least a detached single family house, as described also as example 1 in the technical report to the standard 52016-1, the energy need calculation. And for residential, we also think of a residential block building and for offices also typical office block buildings. So it is not really very exciting architecture, but it is easy to define all the parameters we use in the calculation procedures. What do we expect as output of this project? A set of commented calculations on example buildings and systems that demonstrate that the individual modules work properly, that connection between the modules works, that the calculation procedures fit real cases, as we use real buildings and real input values, that the input for the outer calculation doesn't require a high amount of work. On the contrary, you could say, as we already explained in webinar number 4. And that the procedure is sensitive for different technologies. So you can demonstrate this by applying different technology in the same building. When we finalize this project of the example buildings, there will be a presentation of results of the test cases, the drawings of the buildings and the functional diagrams of the systems, the collection of the used calculation spreadsheets, the set of interconnecting spreadsheets with the preloaded calculation values, and explanatory notes how to use these and observations regarding the results. This will be gradually explained during the next 3 webinars, as you have seen in the announcements of this webinar. After me, we have 2 presentations, one from Dick van Dijk, which focused on the first series of example calculations on the energy need calculation, as described in the EN ISO 52016, starting with the calculation of the heating and cooling of a building. And then Laurent Sokal presenting, you could say, the landing platform for all the energy needs and energy use calculations, the overall energy performance indicator as described in the EN ISO 52000-1, the overarching standard, as this is the landing place for the results for all energy need and energy use calculations. Thank you for your attention, and I want to give the floor to the organizers. Thank you.
Dick, please, you can go ahead with your presentation.
Yes, I'm sorry, I was muted. So good afternoon, everyone. My presentation will be about first example calculations on the energy needs according to the standard that Jaap already introduced before. So here's a slide with my background information. If you want, you can read this when you go back to the recording later on, which will be made available afterwards. And I'll just move on to a more interesting slide, which is giving a overview again on the set of about 50 EPB standards. So Jaap showed you the very detailed slide which covers almost all of the EPB standards. I like to concentrate on a few of these, and first, I'll start with the overarching standard for the EPB set, EN ISO 52000 Part 1. Actually, this is a double-faced standard that has 2 sides. And the first side is actually the first step to take, and that's to establish the overall framework for the whole set of calculations. And by the way, if you are interested in more details on the whole set, you could listen to the recording of the second webinar, which gives you many details on the whole set. So double phased is what I said. So the second phase of the overarching standard is actually the last step of the calculation. So that is the overall energy performance as the top of the pyramid. It aggregates all the data from the heating and cooling, ventilation, mascot water and lighting systems to create an overall energy performance, and then to convert that into primary energy and CO2, but I'll not explain more details on that because Laurent Sokal will do that after me. So what else do we have? So let's look at the core set for the calculation. So now we see the pyramid in full glory. The overall energy performance, as I said, aggregated from all the data of the systems which use energy. So from heating to lighting. And in order to be able to calculate the energy used by the systems, of course, you need to know what are the energy needs. And to calculate the energy needs, you need to know the boundary conditions and the input data. So the core set is described by the energy needs, the ENIs of 5216. Then you have several system standards for heating, cooling, ventilation, pneumatic water, and lighting. But then the second important standard is the ENIs of 52,000 to aggregate all this. So that about the core for the calculation, and then we have also a few post-processing standards. So if you have the overall energy performance or you have the overall energy needs for the building, then you like to convert that into overall indicators or to an energy performance rating. Or here on the building fabric, on the building needs level, you like to have an indicator for the energy needs or for the quality of the fabric of the building. And that's covered in these two separate standards. And why are these separate standards not integrated in the calculation of the needs and in the overall calculation, overall energy performance? And that's because the choices on this level are more policy driven. So then it's more convenient to give the choice to look at these standards, to consider these standards separately. Okay, then we also have pre-processing. So for instance, you need climatic conditions, and we have standard for that. You need the indoor conditions. Jaap mentioned it already. And then you have several standards which give you the input data from products and building elements. And several of these are part of the EPB set, and others are pure product standards, and they are separate sets. So this covers a quick overview. And then, of course, the first question is, okay, but where to start with the calculation? Well, I would say start with the calculation of the energy needs and add to that the overarching EPB standard, so the aggregation and the conversion to primary energy and so on, which Laurent will explain later on. And then, of course, you question, hey, you forget about the systems, the energy use. Well, I don't want to forget about the systems because systems are certainly not less important in the calculation. But if you calculate the energy needs for heating and cooling, you have already a first very important indicator. And in some cases, to add to the energy needs, the system losses may not be very complex. Or the system losses can be added as a preliminary estimation. If they are more complex, you could say, okay, let's start with a preliminary estimation, and you get already a rough idea if you then continue with the overarching standards as I said, as just the core of the calculation. And there's another reason for choosing this priority, and that's because there exists a wide variety of system technologies. Some are simple to describe, other more complex, for instance, interacting with the needs. So it's good to have already the backbone of the calculation and then see, okay, what should I add with regard to the systems. So we start with the calculation of the heating and the cooling needs. And at several slides I have indicated that there is a spreadsheet tool available, and probably in the PDF which comes available after this webinar, along with the recording, you can find the links to it, and otherwise it's not difficult to find the spreadsheet tools and the other locations at the EPB Center website. So, okay, we start with the calculation of the energy needs for heating and cooling, but then how to get the input data for this calculation? Well, I thought I could divide it into 5 categories. So the first category is the outdoor environment, climatic data. The second is the indoor environment. So what are the required conditions of use? Then, of course, the building component data. Not to forget air infiltration and ventilation, and then, well, some leftovers, spatial data. And I start with the assumption that we want to do an hourly calculation. And that brings me actually to a slide which I showed before in the previous webinar, just to remember that the EN-ISO 5216 has a parallel hourly and monthly calculation method. They use both the same input data and boundary conditions. So with the same input data and boundary conditions, you can choose for the hourly condition, the hourly calculation, and you can choose for the monthly calculation. And often it's in the building regulations at national level, they make a choice between one or the other or both that may be allowed for the calculation in the context of the building regulations. Well, the beauty of having these combined in one standard is that the hourly calculation gives you as an extra output the monthly characteristics, which you could use as a basis to validate the monthly calculation method or as a correlation factor to further develop or refine the monthly calculation factor. And of course, side by side, you can see the results of the monthly and hourly calculation. If you do both, and actually in the spreadsheet, both calculation methods are covered. So back to the set of input data. So the first type of input data are the hourly climatic data. For that, you have the test reference years with hourly data for a given region of country. These types of data exist since many years. But they may not, and they are based on an EN-ISO standard, they may not be always everywhere available. Well, for that, the Joint Research Center of the European Commission recently developed a generator to generate typical meteorological years, which are hourly weather data for any location and period of choice. And so that's nice. So assume that we have one of these climatic data files. These will contain hourly solar irradiance on a horizontal plane. Well, for the building, you need not the irradiance on the horizontal plane, but also on vertical or tilted planes, on solar panels, on windows, etc. So for that, we have one of the EPB standards, EN-ISO 52010, part 1, which does the conversion from the horizontal plane to solar irradiance to tilted and vertical plane. And surprise, we have a spreadsheet tool which does this conversion for you, and this is also available at the website. And then new is that we developed a tool to convert the joint research data files, the typical meteorological years, to make them suitable as an input for the EPB standards. And the conversion tool is ready, but it will be made available by the end of October publicly. And okay, then we go to the next one, indoor conditions. So in the context of EPB regulations, the indoor conditions are typically specified by the public authorities, which means they say for a specific building type or space type, what are the occupant schedules you use for a comparison to get comparable results, and the temperature, humidity set points, and internal heat and moisture loads. So these can be set for each hour and each day as input for energy need calculation for different types of buildings. And default schedules are provided in EN 16798 part 1, as Jaap also already mentioned. And we are currently working to develop a use profile generator, which is also a spreadsheet tool. And this will conveniently convert the profiles from this standard or from alternative national profiles into a, so to say, calendar, a full year of hourly input, which you can directly use as input for standards like the energy needs calculation or other standards which need these profiles. Then the building component input data. So it has been explained in the previous webinar that for the hourly calculation, you do not need more input data than for the monthly calculation. So if you want to know more about that, go to the recording of webinar 4. And this is the typical list of input data you need on the building component. So of course, for each opaque construction, roofs and walls, the area, orientation and tilt angle, the thermal resistance, solar absorbance of the external surface, and the type of construction, so rough indication whether it's a heavy, light, homogeneous type or a sandwich type, with thermal insulation in the middle of or on the outside, etc. Then for the ground floor, typically similar data are needed, but you need some extra data, for instance, the ground properties, and you have different floor types, it might require some additional data. This is covered also in an EPB standard, the 13370. This one has been made suitable for hourly calculations, and that's quite important because the ground inertia plays a very important role in this. And because this is also an hourly calculation and it's closely linked to the calculation of the thermal balance and the energy needs for the whole building, this calculation for the ground floor is fully integrated in the spreadsheet of EN-ISO 5216. So you don't need to do a separate calculation, which will be difficult anyway because you have hourly links. Having said that, then we go to the windows. So again, area, orientation, tilt, the U value, thermal transmittance, which is also covered by EPB standard, and the solar transmittance, total solar energy transmittance, also covered in the EPB standard. And then I can reassure you, if you're not so familiar with these, the thermal resistance or thermal transmittance and solar transmittance data, they are very conventional types of information, and usually these are provided by the component or building element supplier. Then the next set of input data are air infiltration and ventilation. The EPB standard EN 16798 part 7 provides the airflow rate, and the ventilation system data are provided by part 5 of the same series of standards, which gives you the ventilation pattern and the supply air temperature and humidity, if not simply the outside temperature and humidity. And spreadsheet tools for these two are also available at the website. So yeah, so you could run these standards and get the input data for calculating the energy needs, but that's another hurdle. So to start with, I would say start the calculation of the energy needs with simplified assumptions of the airflow rate pattern. And then later on, you could add more details by adding these standards to it. And then we have the special components, and I hope you are not disturbed by the noise of a hailstorm, which is just starting here in the Netherlands. So mainly it's about solar shading by external obstacles. This can be remote shadings or from the own building, so side wings or overhangs from your own building. This is covered in the EN ISO 5216. There's a choice between simplified or detailed input. The calculation can be done hourly. And yeah, what about the spreadsheet? There used to be a solar shading spreadsheet calculation integrated in the one on the climatic data, but we removed it from there to keep that one clean, and now we are developing an independent standard spreadsheet on the solar shading calculation, which will use the output from the EN ISO 52010 on the solar radiation data and provide hourly input for the calculation of the energy needs. But the connection has to be made, will be done at very short notice. So that covered the input data. Now something about the status of these spreadsheets. These spreadsheets that are mentioned are publicly available. They can be downloaded from the EPB Center website, and they are mainly intended to demonstrate and to validate each EPB standard. And you must be careful not to confuse the spreadsheet with the corresponding standard. So the spreadsheet might have some limitations which the standard actually doesn't have. So there may be some practical limitations on the input data, while the corresponding standards might give you the full freedom of types of input data. For instance, on the use patterns. And maybe some special features not included. For instance, in the spreadsheet on the energy need calculation, it's a single zone calculation, and it does not have the option to have an attached unconditioned space like a sun space or something. And another important feature of the spreadsheets is that the highest priority was to get the spreadsheet technically correct and transparent. Where possible, all the intermediate results are shown, and moreover, at each step of the calculation, references are given to the corresponding clause or formula in the standard. And that's because the main aim of the spreadsheet is to demonstrate and validate the standard. So this means, unfortunately, that there's a lower priority to have these spreadsheets very user-friendly, and also a lower priority on the performance of the calculation, so the speed of the calculation. So these spreadsheets should not be regarded as tools for daily practice to assess the energy performance of a building. Well, so far about the input data and the spreadsheets. I made here a summary diagram with an overview, but you can look at this later on when you want to view the recording, and I'll continue with a very important part, the output of the calculation for the energy needs for heating and cooling. So if you have done the hourly calculation, you will get the hourly sensible and latent heating and cooling load. You'll get the hourly indoor temperatures, so both air temperature and operative temperature, and you'll get the indoor relative humidity. Of course, you will get the monthly heating and cooling energy needs from the hourly calculation and from monthly calculation. And statistics like the peak load, the load distribution curve, the frequency of over and underheating, quite interesting is to get the energy signature on the energy needs and the key monthly parameters which you could use to compare the monthly and the hourly method. And then it is important to know that the standard can be run in different modes. So the basic mode is to calculate the basic energy loads and needs, so the hourly loads and the monthly needs. But you can also run the standard in a system-specific mode, which means that you can take into account an undersized or an absent system. So for instance, a residential building with only heating and no cooling. You could take into account recoverable system heat losses, which add to the heat load in the building, or an imperfect control. And you could also run the standard in a system design design load mode to calculate the maximum heating or cooling load under design conditions. And of course, in that case, you need other boundary conditions, the design boundary conditions. So enough for all this. And I'll go quickly to the calculation cases. So the first selected building is a detached single-family house. Jaap already introduced this one. And we will run three different climates, as Jaap already mentioned, different energy performance levels, bad and good energy performance, and system-specific input like different sizing of the heating or cooling system, sufficiently sized, undersized, or absent. And I said we will do that. We are running these calculations at the moment, but to be honest, the results of the calculations are currently being reviewed. So I don't think it would be wise to show them now. I will show them in the next webinar together with the calculations where we connect the energy needs more detailedly to specific systems like the heat pumps. So I'll just conclude my presentation with a few examples as just an illustration. So this is just an illustration of the type of hourly results you get. Here you see the set points for the cooling. So during the day and off during the night. And here the cooling load, here very high cooling load. And the indoor temperature, air temperature, mean radiant temperature, and operative temperature. So just as I said, as an example. And another example is to show the monthly heating and cooling needs. Here the heating needs and the cooling needs for some specific case. And you see here very nicely the results from the monthly calculation method and the hourly calculation method together. They look quite nicely, they fit quite nicely, although if you look at more in detail here, you would see that the monthly calculation is 50% higher than the hourly calculation. But this might look good for the comparison between the monthly and the hourly calculation method, but be aware that the match can be quite bad. For instance, if you have more complications brought in, or if you have an undersized system. If you have an undersized system, the monthly calculation method would not detect it, would still remain the same, and the hourly calculation method would give much lower cooling needs because the system cannot cope with the needs. Next is just a illustration of the calculations with different sizing of the heating and cooling power. So this is one with sufficiently sized system here, almost sufficiently sized here, an undersized system here, absent system. And which gives you this kind of additional results, which are shown also in the spreadsheet calculation. And here I brought them the four cases together. So the heating load duration curve, if you have sufficient power, heating power, then you have only a few hours at maximum heating power. Here with an undersized system, you have more hours with the maximum heating here, in even lower power for the heating system, and you see a quite high percentage of hours with maximum size running, and that of course is reflected in the hours that the operative temperature is not meeting the required 20 degrees Celsius. So if the system is absent, you have many hours with too low temperature, and if it's undersized, you also have many hours undersized system. Undersized, in case of undersized system, too low temperatures. And on the other side, on the cooling load, if you have an undersized cooling system, the same here. If you have an undersized cooling system here, you would say 10%, in this case 10% of the hours it runs at the maximum cooling load. And in that case, it's the green line here. You'll have high temperatures, so you exceed the maximum temperature set point, which was in this case 24 degrees. So this is actually just a teaser for the next webinar when we'll show more results. And this brings me to the last slide to conclude. Well, EN ISO 5216 Part 1 is one of the core EPB standards for calculating the overall energy performance of buildings. There are tools available to perform the calculations according to the standard, and these are capable to demonstrate the functionality and the sensitivity and the usability, as Jaap already introduced in his introduction. And there are tools and example calculations being made. So this is work in progress. So some of the tools are available, others are in under development, and so this is work in progress. And this concludes my presentation, and I thank you very much for your attention, and I'll give the floor back to the organizer or to Laurent.
Okay, thank you, Dick. Good afternoon, ladies and gentlemen. Now it's my turn to speak about EN ISO 52000-1. And this is my background, and you will be able to read this later on the records. I'm just coming from Italy, self-employed and active in a lot of work on the standardization. So it has been already said that 52000-1 is a double phase standard because it's used before, it gives a structure, and after that the calculations of building envelope and the technical system is finished. And the main task of 52000-1 will be to determine the global balance of electricity, which can be delivered from the grid, produced on site, accumulated on site, and exported to the grid. And you need to do this after you know all the uses and all the generation possibilities. So it's the last step of the calculation. And then we'll determine, once you know all the energy flows, you determine the overall weighting of the energy carriers. And here we focus on the final balance. So how to stress this module alone? And of course, you need to take into account that the calculation starts from, let's say, the comfort condition, the environment. This determines, together with your building, some needs. And the needs, typically, it's an energy, but sometimes it's also something else. The needs for ventilation is an airflow or an air volume or a light flux and so on. And then you will have a result, systems except generation, and we will see. And this is usually quite simple. It's just distribution, emission, so some auxiliary energy, some losses. Then you go to a need of heat extraction, and electricity. Overall, you need always something like that. So you will ask to generators to provide the heat or to extract heat or to provide electricity. and this will result in a need of energy carriers. And here comes the 52,000 that will weight your energy carriers and provide you the final result will be weighted energy. So this is more or less the calculation chain that we will see, and we will have to prepare some mock-up of this first part of the chain because we want to test the final part. And the role here you have, I put an evidence on the role of the 52,000 is just the electricity balance and then the energy carrier weighting to get the weighted energy. And you've seen also the nice slide about Hogeling, and more or less this is the same slide which is turned upside to the right, and this is the new interface for the spreadsheet which will illustrate how 52,000 works. And you can recognize that here you start from the needs. Here in this area we will define needs, and typically this spreadsheet allows you to it makes a simplified simulation of everything that happens in your technical systems, and based on your needs you load this with some profiles and you have some controls to be able to modify them quickly, just increase or reduce, and so that you can prepare and then experiment. We'll have a look at this in some more details. And here you have the needs which are organized by EPB services, this yellow area. And here you have the first part, which is all the technical system without generation. It's just distributing heat. For example, here you have this rose color. Here you have some different possibilities to generate heat. They are combined together so that you provide heating, or you are heating your domestic hot water store. And for example, here you have also the connection between the ventilation and the rest of the installation, because you typically have an air handling unit that provides a flow of air, and it consumes electricity, and it requires heat and heat extraction for the coils. And here you might have also cooling, and the blue arrows typically are electricity. Here is heat extraction, and this is more or less heat. And here you have the generation subsystem. So for each kind of technology, you might have some parameters, and you know the input and the output. And here below, you have the energy, the electric energy balance, so that you can calculate how much will be delivered or exported to the grid. And here you get the results of your calculation in terms of weighted energy performance. And this is just the description. So there's the list of all energy carriers that cross the assessment boundary. So this is a scheme, and this scheme, it will be the new interface, and all the figures that you see here, they can be the result yearly, it could be a month, it could be 1 hour, and you just select this. And you have a lot of controls to enable to select your configuration so that you can quickly modify and test different alternatives. So the EN ISO 52001 competence is just this area. We are just waiting, we are doing the balance for the electricity, but we need all these kind of things to be able to test it. And that's why we have to build around a simulation of the real building. And shortly, with time, we will interconnect also specific modules so that we can test, as Dick explained, part of this modular structure. And this is just a reminder. So I spoke a lot on this diagram, and just to remind, this is the area of the needs. And if we are a little bit practical, we know that the needs, they are determined by building envelope and use, and some can be reduced. For example, you can insulate your house and you reduce heating, typically in our climate in Europe, and others are quite difficult to reduce. At domestic hot water, you need it, full stop. Lighting, cooling, and ventilation as well are not so easy to reduce by the building envelope. And natively needs may not be energy. So, for example, ventilation is the volume of air, and depending on the time of the year, you need a different amount of energy for air treatment and for moving air. Here is the area of system except generation, so this is not very complicated. There are some simple parameters to adjust this for the testing purpose. And here, which is important is a generation conversion and the choice of the generator to provide the required heat and heat extraction and electricity. This will determine which energy carriers are required and their amount. And typically, it turns out that what is important is to know how much electricity you need, which can be grid or produced on site, grid delivered or produced on site. This is the alternative that is given when you have electricity, or how much fuels are using, which in turn can be fossil fuel or sometimes biofuels. Electricity balance, and this is needed to take into account the used electricity. And typically you start with the used electricity. It's a result of the calculation of your systems. You take into account the produced electricity, if any, that could be typically PV, cogen, sometimes wind turbines. And based on that, you have to determine how much is immediately used, so just use into your systems, how much is grid exported, how much is delivered by the grid. And you might also consider having, it's an emergent technique, having a battery, so you are storing your electricity and then reusing it later on. This spreadsheet has been enhanced to include also the possibility to simulate also a battery. And at the end, you get the weighted energy performance. Just to be aware, if you will use this spreadsheet, you first have to define your condition around for the operating condition of your building and systems. And when you do changes, you have to perform the calculation to see the right figure as a result of the overarching standard processing. Here just some details about the electric energy balance. And you see, for example, an example of the options. Here you see, for example, the PV, and this is an example of the controls that will be available. Here you have the PV, and you can select how much kilowatts, and the profile is given by the location. And here is the selector where you can find your location. So here you can see only in this moment, this slide was captured with the yearly results. So 3 kilowatt peak, and you get a result of 3,200 kilowatt hour along the year. But you can show also intermediate results. And as usual, you have electricity which is used, you have electricity which is produced, and the produced can be immediately used, stored, or exported. And when you need electricity, it can be what has been produced, battery charge, discharge, or grid delivered. It looks like simple, but if you have to handle this kind of thing with all possible options, then it makes the standard a little bit longer. But here you have practically very few choices or parameters. And here are the parameters which are important when using the 52,000. And the main parameters, of course, are the weighting factors, but typically they are decided by member states because, and these are not that different from, maybe they are different from country to country, but they are decided by member states. There's no, let's say, freedom of choice for regulatory purpose. What is important also is what is very impacting the K exported, which states if the exported energy is accounted in the energy performance of the building. And this also is a consequence of the choices of the regulation when determining the energy performance. Then you have other parameters, for example, the RER per minute, renewable energy ratio perimeter, which defines which renewable energy components are taken into account when you calculate the overall renewable energy ratio. And potentially you might have a matching factor for the monthly method to take into account mismatch of electricity use and production. We will have a look at this in some details. And these are quite important parameters because these are options that more or less are given in the regulation. And in the past, their definition was not really transparent. With this standard, they are making obvious and documented and transparent. We said that influence is the so okay, nothing special here. And what is very important is the weighting types. How can we weight energy carriers? This standard will provide you with the result for 3 weighting. You might weight energy carriers as primary energy. And again, primary energy can be non-renewable, renewable, and total. But you also have CO2 emission and cost. This is done simultaneously by the spreadsheet. And here you have the link to our short videos to go into more details about primary energy. And you have also a possibility that the factors for exported energy may be different from those of imported energy delivered, let's say delivered energy, and time dependent. An example is the cost. The cost of electricity can be typically an hourly profile, depending if it's peak or off-peak hours or whichever combination. And this parameter should be given, of course, nationally, and typically they reflect the origin of the available energy carriers. And typically they come from member states' regulation. And here is an example. When using this standard, actually, you just select which set of parameters. So these are the default for Annex B, but here you might have also the choice for national parameters. And you at once give, here is really a short extract, but for each that are selected in one shot. Here also the parameter K exported, and here again you might go for details to the short video for the explanation. And it is a very important parameter, one of the most impacting. And the K exported 0 excludes, this is not weighted, this is a mistake, this is exported energy from the energy performance. And K exported 1 includes the effect of exported energy into the energy performance of your building. And this is very sensitive, and this has also other consequences. If you select to incorporate the exported energy into the energy performance of a standard, you allow cost compensation between energy carriers. So electricity export can compensate a fossil fuel use, and compensation between electric energy produced and used at different time. So if you select K exporting equal 1, on fact, the grid is like a huge battery. So in this evaluation, the battery has no effect. This is important to understand, so to know which is the effect of these parameters. And what might happen also is you might have a different decision for the K exported for the different types of weighting. So the influence of 52,000 depends on the choice of the generation technology. Find which energy carriers may be used. So where you are going to as values of the weighting. There's an impact. So it has an impact on the achievable performance, especially in terms of renewable energy use. Of course, if you have a boiler, no chance to have renewable. You can use a heat pump, and then it's more effective. The efficiency is higher, and of course, if correctly used, and you have also a contribution in terms of renewable energy. So depending on the choice of the generation system, you have different results. And how does the 52,000 influence? Basically, the type of building and climate gives the first mix between heat requirements. So this is of course used for heating, cold climate, or for heating. When you have a cold climate, uninsulated buildings, low use buildings are shifting the need of your building to heat. And generators typically for heating can use both fuels or electricity. You have the possibility to choose what to use. And then you have heat extraction, and typically it's for cooling, of course, in warm climate, insulate and use intensive buildings. And if your building is use intensive, you will have probably cooling needs, even if the climate is not so hot. And then you need electricity. And typically you have a direct requirement of electricity for mechanical ventilation, lighting, transport, auxiliaries, which are required by the system. This is the first mix, because by the change of the generator, you might achieve some heat or some heat extraction by using electricity. And then this makes a difference in the mix of the carriers. So here is just a reminder of technology. I won't go through, just let you as a reminder. These are the main. And of course, heat pumps and chiller may use electricity for heat and heat extraction and shifts the balance of energy carrier towards electricity, which is what we tend to do lately, because electricity you can generate it on site, and this can be very practical. And other function of this EN 52000-1, of course, you are building the renewable energy ratio indicator, and here you have the possibility to define a perimeter, which contribution to take into account. For example, don't take into account distance, because you want to take into account in the renewable energy ratio, this might be one purpose, what is the effort done by the building. So you exclude the renewable, which has been important. You take into account, you show only renewable produced on site to show which is a contribution of your building. This is one reason. It depends on what you want to indicate with this indicator. And the fact is that sometimes the renewable energy ratio is used as an indicator, but if you as a regulation requirement, but in this case, this may limit the choice of the generation technology. Then you have a matching factor between produced and used electricity to be taken into account in the monthly calculation, because you do not know if electricity generated when used. And you might set up a priority of on-site electricity use. If you have several generators, you need a priority to decide which is used on-site and which is exported, and the allowed use of generated electricity. Because some countries, for example, exclude from the energy performance certain uses of on-site generated electricity. For example, PV used for direct heating is not very advisable from an energy point of view unless you don't know what to do about your PV. There are better uses than direct heating. So that's to say, you will find some options for all this function of the EN ISO 52000-1. Why hourly parameters? That makes also one of the few tricks in the equation, as weighting factors may be time dependent. And of course, one of the most obvious example is the cost of grid electricity, which is typically time dependent. But also the electricity weighting factor may be time dependent. Which grid generators are in use at different times? So what's powering the grid at different times of the day? This might be also a reason to have time dependent electricity weighting factors. And also the effect of exported energy may be time dependent. So the standard is clearly supporting this as hourly parameters. So here we go to a simple example just to get the first flavor of the calculation. It's a simple house with a single family house, a gas boiler and split air conditioner, some thermal solar for domestic hot water, reasonably sized, 3 kilowatt peak photovoltaic, and KX41 and default conversion factor from 52000-1. If you do this, this is what will be the result in our scheme. So you need the heating needs, about 10 megawatt hours per year, and we have 6,000 hours of operating. We have some domestic hot water. You see that more or less half of the domestic hot water is covered by the thermal solar. The heat pump, the power is set to 0. This allows to simulate that there is no heat pump, it's just a boiler. So logic is, if you have, there is a priority between generators, first the cogen, then the heat pump, and then the boiler, and the boiler takes whatever rests from others. And you can see here the weighted energy performance. And you might notice, for example, that here you have about 15 megawatt hours of gas, and this turns into 16 megawatt hours non-renewable energy, and the energy performance as non-renewable is lower than the gas. Why? Because it's K exported equal 1, and so we are including into the energy performance what the exported energy. And here you have the aggregated results. This you can do with all the results. You get the hourly results, but it can be also interesting to have the sum. These are not monthly calculation results. These are monthly aggregated results of the hourly calculation. And you see here the result for the weighting, and you see non-renewable primary energy, renewable, the total primary energy, the CO2 emission, 2 tons, and the cost. How much does it cost to provide EPB services to this house? And here you have some details about the electric energy. And you see, for example, that even in the month where you have EPB uses, you have produced electricity, you produce more than what is used, but indeed something is exported to the grid because you have not the simultaneity. And you can see also here, important, you see here this month, this is the result, these are the results for the summer. And in summer, we have a lot of PV, but there's just a little bit of air conditioning. So we are exporting PV energy. So we are benefiting, we are reducing our non-renewable primary energy performance because the exported electricity is accounted as a reduction of the amount of primary energy needed. And as well, for example, we have this is accounted for emission, and maybe this is a more understandable. Of course, you are selling your exported energy, so you're benefiting in the costs. Whilst you paid in winter, in summer you can benefit, so the result is the net. That's the meaning of K exported equal 1. You are compensating the cost of serving your house with the benefit of selling the exported energy in terms of money, in terms of CO2, or in terms of renewable primary energy. So in the yearly diagram, that's just to show what I told you already. You see here the value for the gas, the kilowatt-hour gas input to your boiler. Here you have the corresponding primary energy, and you see that the weighted performance is lower than the gas alone. Why? Because we compensated in summer. This is the effect of K exported equal 1. And just to make another extreme, in that case, we are going to the same example with a heat pump and PV, and the K exported set to 0 in this case. And what we will see, in this case, you still have something for the gas, because for the calculation we take into account in these modules, I take into account the maximum available power, which is depending on outdoor temperature. So there is a little residue of operation for the boiler. Nevertheless, here you have the results. In this case, K exported equals 0. So if for the heat pump, you see that you need our non-renewable kilowatt hours. Sorry, here there is something not correct here. Because it's 1 month probably. No, that's 1 year results. Okay, and you see here the weighted energy performance, which is quite lower, and the cost even is higher. But if we go to the result, you will see here that in no month we have a negative value. We have no compensation, because with K exported equals 0, we are accounting everything that is needed to provide the services for our house, wherever they do come from. So here you're paying some electric energy. Of course, we have PV, but at some time you need indeed some electricity from the grid, and this is accounted for in this calculation. No negative components, only the cost of what is used in the building is accounted. So no benefit from exported energy. And here, for example, last 2 slides, it's just to show the example of the hourly calculation. It's a summer, it's beginning of cooling. The blue is the EPB uses, and you see the cooling, which is increases. And then you have these kind of peaks, which typically are for the domestic hot water when you have some need, or for lighting. And you see here the produced electricity is your PV. And of course, here we have a lot of PV, no cooling, probably it was not so hot a day. And you see here, but nevertheless, you're not matching exactly. And probably this was a little bit more cloudy, so you have not enough PV during the day. So you can see if you have K exported equals 0, here you have to buy electricity from the grid. And here this is exported but discarded from the count if K exported equals 0. Of course, if K exported equal 1, you benefit from the exported energy, so you will have a compensation. And even another example, here we are in winter, so it's heating plus domestic hot water with the heat pump because no solar. So you see the peaks when the domestic hot water has to be provided. And probably here it's cloudy, and then here it's sunny and cold. And in this case, you see, even in winter, in some hours, you have more PV than the required power for your heat pump. In case exporting, if it's case exported equals 0, you will take into account that this is not used in your building, this is just exported and not accounted for. So you see the importance of the hourly method to check the real match between production and use of electricity. So, and here we go to the conclusions. And this was, of course, just like Dick said, it is just a first glimpse of what you can see when doing the calculation. And of course, now it has been done with well, it was actual profiles coming from a calculation, but not really all from the same exactly the same buildings. This will be assembled, so it is reasonable. So the conclusion, there are some parameters, not so much parameters, that really impact energy performance. And the most impacting choice is the K exported. And there are member states using both, so this might be an issue. This is now made clear. And here you have a link to the short video with more details about this feature. And the achievable performance range depends on the generation technology. And this you see when you come to the last balance. That's the generation technology has an impact on the distribution between fuels, fossil fuels, and electricity. And the timing is more and more important. So the hourly calculation is needed if you want to capture correctly when you have power and when you have not enough power. So, and this needs modern calculation tools and trained experts to understand all these small details, but that build up, because efficient building is building using few and less energy or little amount of energy, but any small waste or any detail is quite important. And this concludes my presentation. I thank you for your attention, and I give the floor again to the organization. Thank you.
Thank you. So we can start the Q&A session. The first question is, can we use an ISO 13370 for monthly calculations?
Maybe for that's a question for me. Yes, that's the standard on the thermal transmission losses through the ground floor. And the original standard was only for monthly calculations, and now the standard is suitable for monthly calculations, but also for hourly calculations. So it can be done both.
Good, thanks. Second question. We are familiar to use US and ASHRAE standards mostly because of using related software such as Carrier, HAP, Design Builder, etc. As far as I saw, using the EPB standard set will give us more flexibility, more systems to be imported into simulations, and especially converging to the primary energy use. But I saw that you are creating some spreadsheets for each step of the calculation. Is there any commercial software that we, it's a designer and consultant talking, can use commercially, or are there any studies to convert those spreadsheets to commercial software? Then an ASHRAE 140 compatibility report may be generated to convince the government to use these EPB standard sets.
Well, who's starting to answer this complicated question?
Maybe you can start, Jaap, with a general general view.
Yeah, in general, if you speak about software you refer to from ASHRAE and from suppliers, this is mainly from suppliers focused on the cooling load calculations, which can be done also as Dick explained in the Vision 2016. But if we talk about energy calculations, the software that is available, let's say at ASHRAE level, so international also used. The standard 90.1 is an entirely different approach. It is a prescriptive standard that contains requirements on products, which is a road we left in Europe many years ago. So our set of standards, EPB standards, are performance-based, which is a guarantee for innovation and further development. So I should advise the users of those prescriptive standards to look at the set of EPB standards. This leads also to the question: is there software available for in Europe for EPB standards commercially? Yes, there is software, but the software in different European countries is based on national procedures that have been developed. This software is based on their national energy performance procedures. Many claim that these national procedures are according to the EPD standards. Well, it's very difficult to judge, but we assume that in developing those national procedures, they used at least the EPD standards as a basis. I know that some of the software used in several countries is based on the previous set, but it's mainly they use monthly approaches, more simplified, and some updated their procedures on basis of the current set, incorporating also the national choices and certain levels of simplification, which is acceptable in our view on using the EPB standards. And some countries in Europe can state that they follow with their national available software the current set of standards, but perhaps not for the fully 100%. And they are they are still working on it to achieve that level. And well, if I speak of software available on national level in Europe, we have also to realize that several countries have software certification schemes that are in place to sort of certify the software on their national market. But again, this software is based on the national procedures. And yes, it should be nice that there is a European, you could say European software based on the EPD set of standards. There are some initiatives to develop it in the framework of Horizon 2020 proposal, but at this moment I cannot refer to it as something that has proven to follow all the standards at this moment. This concludes my long answer. Perhaps Dick wants to add something to that.
Was quite a complete answer, but I also think I understood that the question was also about the capability of HVAC 140 to be used to verify software. Well, in that context, I can say that the EN ISO 52016 Part 1 has been validated against the relevant cases according to the ASHRAE ANSI 140 standard. So for those of you who are not so familiar with the number, these are the best test cases as originally developed in IEA projects.
Yeah, perhaps it's good to say that our standard performs in that respect.
Yeah.
Thank you. Another question, when will we integrate future climatic data in the calculations?
I could say something about that. A set of EPB standards does in itself not contain the standards to generate the typical or test reference years, as I mentioned in my presentation. But so these are based on the existing ISO standard. I always have to look up the number. So the EN ISO 15927 part 4, which are mentioned in one of my slides. And actually that standard is currently under revision in a ISO working group to make it more suitable for the climate change. So to enable also to generate climatic data which take into account the near future changes, because if you want to design a building and the building will last for say 50 years, then you do not want to have a design for the current climate, but you want it to be designed and also the energy performance to be assessed for somewhere in the future, say in the average lifetime of the building. So that's the idea of the revision of that standard on how to generate test reference years.
Thank you. Another question. Are there any plans to show a full example on how to use all the spreadsheets for an example building, starting from scratch to the final results? Right now, it's impossible to understand how to use them fully.
Well, when I start to answer, it is the idea, as I said in my introduction, that we will produce an example to use a complete set of standards for a building. That doesn't mean that we connect all spreadsheets in an automatic way. That's not possible, but we will calculate, we will produce an example building results as such. But perhaps Dick or Laurent could add something to that to explain it more.
Well, I think the answer is already more or less clear. So the spreadsheets are not designed to work together with all the possible connection, with all the possible modules. And the case study will be a collection of spreadsheets used one at a time and transferring data manually, because this is the idea, to show that this works. Then it is a task of software developers to provide with commercial software for productive purpose. Here, the scope is not productive, is to, let's say, fine-tune these standards and to show that it's okay for going to practical use. And the advantage, by the way, is that when you test a module, you have a full insight of what happens on every calculation interval via the Excel. But of course, this is not what you need in everyday life.
There is another question in this topic. If you say that the spreadsheets are not supposed to everyday use, what software is able to substitute or can be used for the everyday work?
Well, as I said before, we are not able to identify everyday software that meets all the requirements of our EPB standards. So there is, as far as I know, not a declared software package in the European market that meets the set of EPD standards at this moment.
As far as I know, there are 2 or 3 software in Italy that have only a part of the energy need calculation according to 52016. but this is just not for, of course, for a regulatory purpose.
Yes, and I remember when I was at a workshop in Germany to discuss the approach of the national DIN standard on energy performance. That the claim was that the software based on this was following several European standards for, let's say, 95%, some for 80%, some for 30%. So it's again a national procedure, and so it is very difficult to say it's covering the European set.
Yeah, that's clear. So there is another question. What is the planned time frame of developing, testing, and combining all the spreadsheets? In general, is there any planned date when the final spreadsheet version will be approved and presented at the EPB Center?
Well, the planning is, as you can also see on the webinars we organized, that we will, by the beginning of next year, finalize our webinars on this, and then we have to finalize the reports on all the example calculations before September next year. But preferably earlier. It depends a little bit on the progress and perhaps the feedback we get. But I expect in half a year's time we will see a lot of concrete results on our website already.
Thank you. So maybe one last question. This is for Dick. If you want to try out the spreadsheet on an ISO 52016/1, is it quite complex? Would it be possible to make a user guide?
Yeah. Well, it's true. As I mentioned in my presentation, the spreadsheet shows all the intermediate results, and therefore it might be quite difficult to find your way through all the different sheets which produce these results. So that's the backside of being transparent in all the details. Yeah, we are thinking of preparing a guide, and possibly it could be in the form of a short video to have a hands-on demonstration of how to work with the spreadsheet. Yes. So this encourages us to go for this.
Okay, thank you. So there are no more questions, and I would close the Q&A here. So thank you to the panelists, and thank you to the audience. Finally, I remind again the next webinar, which will be the 8th of the EPB series, and it's scheduled on the 20th of October at 12. And you'll be able to register very soon. So thank you all.
Thank you for organizing.
Thank you. Goodbye.
Goodbye.
Thank you all.